Good morning, gentlemen. Today is Friday, May the 29th, and today we are going to start the next unit in our little adventure in physics. And this is all about modern physics. And so the things that we're going to study in this unit are actually around 100 years old or so, maybe 130, 140 years old maximum. But we're going to start with the idea of the dual nature of light. For years, it was debated whether light was a particle or a wave, and or which one it was. And the arguments went back and forth and back and forth. And depending upon which physicists were most popular in that day and age, that was kind of the way that the wind blew. But in reality, this is obviously not the way that science works. So what we did was, let's start with a history lesson first. All right, on the dual nature of light. We begin with Joe Newton. Okay, now Newton was obviously a very famous physicist, even in his own time. And he was of the opinion that light was composed of very tiny particles, right? That's what he was certain of that. And so, and he had a lot of evidence to support that hypothesis. But he actually squelched all opposing research because he was the president of the Royal Society in London, and therefore whatever he said pretty much went. And so he won out over contemporary wave theories because of who he was. Now, along came a guy by the name of Joe Young. And he pointed out, and this is after Newton's time, but Young pointed out that diffraction, interference, polarization, and the Doppler effect could not be explained by light as a particle. It could only be explained if light was traveling as a transverse wave. And that is kind of what we finished talking about when we finished the unit on wave motion. All right. So Young kind of turned the tide a little bit and pointed out that, Newton might not have had all his ducks in a row here. Then along came Joe Einstein. And in the 1930s, he was working on a number of things. But one of the things that he was able to do, excuse me, was to explain what's called the photoelectric effect. All right, the photoelectric effect. We'll talk about that in just a second. But in essence, the photoelectric effect cannot be explained by wave theory for reasons that I'll show you in just a moment. Okay, so let's talk about this photoelectric effect, shall we? In 1905, all right, which is, by the way, the same year that Einstein published his theory of special relativity, although this is not the theory of special relativity. But prior to this, it was known that light can cause certain metals to emit electrons. So the way we show this is, I don't know what just happened. So we have a metal. So this is a, nope, I'm on the wrong page. Okay, so here's a metal plate. We're going to call this the collecting plate, okay, or the electron emitting. I can't write that. What am I doing? I'm just going to erase that. But this is the electron emitting plate. Anyway, so we're going to attach this to a circuit, all right? And so so here we are. Here's the plate. I'm going to attach this to the negative end of the battery. And then here's the positive end, right? So negative and positive. And so all the electrons that this plate wants are there, okay? Now, on the other side, I'm going to have the collecting plate. Okay, so this is the emitting, and this is the collecting. Now, what happened is that light waves came in from, well, actually, let me finish drawing the circuit here. And so here it is. All right. So what happens is that light waves come flying in. And so here's my light waves. Da, 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 boom. And they strike this. And what happens is that electrons are emitted. All right. And these electrons, I'm going to draw them as little green. Nope, that's a lousy color. Let's try a different color. Let's try blue. Little blue dots. And these blue dots are moving in this direction, toward the left in this picture. The light strikes the plate. The plate emits, the light is absorbed by the plate. The light emits electrons, and then those same electrons are grabbed up by the collecting plate on this side and returned to the positive portion of the battery. Now, if you, crying out loud, if you also hook up a voltmeter or an ammeter here, okay, then you can actually measure the amount of current that is being produced. All right, now this is an interesting aspect, because what we can do is, if we were to graph this relationship and put the amount of energy on the left side, and this can be measured in voltage, current, kinetic energy, that sort of thing, and we put the frequency of light on the x-axis, what we end up with is a graph that looks like this. Dun, dun, dun. And so the graph is horizontal for a while, and then all of a sudden goes up at a in a direct proportion kind of thing. Now, this point right here is what we refer to as the threshold frequency. All right, the threshold frequency, which we refer to as F sub 0. And the interesting thing about this is that light of a frequency that is less than the threshold frequency doesn't emit any electrons at all. There's no electrons. All right. But once you hit that threshold frequency, now all of a sudden you're emitting electrons. And the higher the frequency, the greater the energy that those electrons have. And again, the energy is measured in terms of voltage or current, however you wish to do this. All right. So keep these two diagrams in mind as we move through the remainder of this lesson. All right. So what exactly did Einstein, or was Einstein able to show in terms of this photoelectric effect? Well, we've already determined that no electrons are emitted, no matter what the frequency, or I'm sorry, the intensity of the light. So very, very bright light, very, very dark light, it didn't really matter. No electrons are emitted, no matter how intense the light, unless the frequency of that light is greater than a certain lower limit called the threshold frequency, F sub 0. And of course, if we go back to our diagram, the threshold frequency is right there, okay, whatever that happens to be. Okay. Now, this does not agree with wave theory, all right, because the wave theory says essentially that light of any frequency should be emitting some electrons, at least some electrons, even if it's just a few, all right, because the electrons will be sitting in that collecting, or the emitting plate, and the more energy they absorb, sooner or later they're going to reach the point where they emit an electron, okay. This idea of the threshold frequency indicates that the light must be a particle, All right, there has to be enough momentum of the light actually striking the electrons to dislodge the electrons from the atoms that they're being held on. Okay, so um, another interesting aspect here is that as the threshold frequency, I'm sorry, as the frequency increases above the threshold uh, frequency, the kinetic energy increases. So again, here's your energy on the y-axis. Here's your frequency on the x-axis. And if we draw the graph again, this is here, right here is the threshold frequency. I'll call it F sub 0. All of a sudden, bam, we end up with a direct proportion here. Now, the in terms of energy, and sorry about drawing that graph in the wrong spot, but the minimum amount of energy required to remove an electron from a metal is called the work function. All right. In other words, how much work do you have to do on an electron in order to remove it rather, from the atom that it's held by? Okay, we call this the work function, all right, which is also sometimes abbreviated as W sub 0. Okay, and because it's related to the threshold frequency. All right, we'll get to all of that tomorrow. Well, maybe not tomorrow, but actually today's Friday, so no, not tomorrow, but soon, after we get through what we call quantum theory. In any event, that is the lesson for today. Uh, the idea that light is actually a particle that is traveling as a transverse wave.